All right, today I will be teaching you how to calculate confidence intervals. The confidence interval is a probability that confidence intervals are the probability that a population parameter or proportion will fall under a specific set of values using the population mean and margin of error, i.e. a 95% confidence interval means you can be 95% confident that the true mean falls in this range of data. The confidence interval for solving the population mean is the first one that I will be doing. The sample mean X bar is the point estimator of a population mean. And so I've just gone ahead and set up an X bar or population mean of 57.8, which I will be using in my later example. And so to be able to actually perform a confidence interval for a population mean, it must satisfy a couple of qualities. The sample must be a simple random sample of a population, regardless of sample size. The population must be normally distributed, and you must know the standard deviation. So I've gone ahead and listed the standard deviation that I will be using, 12.4. And so a confidence interval's formula is X bar plus or minus margin of error, which is the z-score of the significance level, or alpha, divided by 2, times the standard deviation divided by square root of sample size. And we will move on to the example. And so I have gone ahead and listed out my example at the bottom. This is the complete solution, but I'm going to go ahead and work it out for you so it makes sense. And so we'll start with, just go ahead and write the mean, 57.8 plus or minus, and we'll leave that until the very end. We're going to go ahead and just work on solving the margin of error. We're going to take the z-score of 0.05 divided by 2, or the z-score of 0.025, which will give us the common value of 1.96 on a standard normal table. I will show you that in a second. I have a standard normal table on the next slide. And so we'll add that in as 57.8 plus or minus 1.96, our confidence interval z-score. And then for the second half, we will do the square root of 57 times the standard deviation, we will do the standard deviation, 12.4, divided by, not multiplication, divided by the square root of 57. Which gives us a long string of numbers, we'll round it to 3 places, 1.642. Oop, that's not good. We're just going to ignore that. I will clear the screen in a second as soon as I get that written down. So I'm going to have to clear the screen because I messed that up and I'm not redoing this. 57.8 plus or minus 1.96 times 1.642. And so 1.96 times 1.642 equals 3.218. And so the confidence interval would just be 57.8 plus or minus that margin of error of 3.218. And so as I was explaining, here is the standard normal tables for z-scores and the common values for z-scores. I think the common values are very helpful because for the most part, with confidence intervals, you will just be using these sets of percentages. And so for that 95% confidence interval that we just performed, the z-score was 1.96. And that's how I got that. On to the next one. So now I will be explaining confidence intervals for proportions. For proportion confidence intervals, you first need to find the p-hat or proportion to use as your point estimator, the same thing as X bar in the population mean. To calculate the proportion, you need to divide the X value by the N value. The X value is the value of sample. The X value is the value of the sample that proved the point that you were trying to prove true. The N value is just the overall sample size. And so for my example, I found that p-hat was 152 divided by 200, which equals 0.76 or 76%. And since this is a single estimate, it's not a truly accurate proportion, but these numbers will make more sense as I get into my example. The meaningful requirements for proportion is that the sample size must be no greater than 5% of the population. And this little equation right here is just to determine if the proportion is normally distributed. And so I will go ahead and calculate that out for my equation. I'm just going to estimate on it because I know it's over 10. So we're going to do 200, which is the sample size, times 0.76 times 1 minus 0.76, or 0.24, and that has to be greater than 10. And I've already done this in my head, so I'm going to go ahead and just tell you it was around 32 if you were to math this out, which means that is greater than 10, and we are in a normal distribution. And so here's the formula for a confidence interval for proportions. It's pretty similar to the population mean, but it's slightly different. You're going to take the proportion plus or minus the margin of error of proportion, which would be z value times the significance level divided by 2 times the square root of the proportion times 1 minus the proportion divided by the sample size. And so we're finally on to my example. My example, I just set up a random situation, a scenario. In a recent poll of 200 households, 152 of them have children. Estimate the proportion of households that have children using a 95% confidence interval. And so I've listed out what I already found to be the proportion, 0.76, the sample size of 200, and I've just gone ahead and rewrote the formula again on this page. And so we can go ahead and start writing out that formula. So p hat 0.76 is known, plus or minus z times the significance level of 0.05, which we find by 100 minus 95%, which would be 0.05, divided by 2. And then we'll multiply that by the square root of 0.76 times 0.24, or 1 minus 0.76, divided by 200. All right, so as for the same as the population mean, the z-score times 0.05 divided by 2, we can check out those common values on the normal table, and that would give us 0.76 plus or minus 1.96, as we found on the last problem. And so for this second one, you're going to need to break out your calculator probably. I don't know many people that can do that in their head. You're going to want to do the square root of 0.76 times 0.24 divided by 200. And you want to make sure that's all in the square root symbol. That will leave us with a long string of numbers of 0.0302. And all you need to do now is multiply the z value, 1.96, times that long string of numbers, 0.0302. And that will give us the margin of error. And so the final answer for a 95% confidence interval will just be 0.76 plus or minus 0.0592, which is our margin of error. And I hope that helped explain some confidence intervals to some people. I know that can be a confusing thing when you're looking at percentages, but once you break it down, it's not too bad.